Let's see some example of partial order relation. First example, show whether the relation x comma y belongs to R if x is greater than equal to y defined on the set of positive integer is a partial order relation. So here consider the set A of positive integer A containing the element 1, 2, 3, 4. So these are the positive integers. Find a relation for this set such as R is equal to 2, 1, 3, 1, 3, 2, 4, 1, 4, 2, 4, 3, 1, 1, 2, 2, 3, 3 and 4, 4. These are the elements of relation R. Now we know that relation is called as partial order relation if it satisfies the properties, that is reflexive, antisymmetric and transitive. So if these three properties are satisfied, then that relation is called as a partial order relation. So what is exactly reflexive property? So relation R is reflexive if A related with A for all A is belongs to A, then that relation is called as a reflexive relation. Relation R is antisymmetric, that is A is related with B and B is related with A, then A should be equal to B. Then that relation, if it is satisfied for all these pairs, then it is called antisymmetric relation. And relation R is called transitive if for all A related with B and B related with C. If A related with C exists, then it is called as a transitive relation. So in this given relation, we will check one by one these three properties. First, reflexive. The relation is reflexive as for every A belongs to A comma A belongs to R. That is 1, 1, 2, 2, 3, 3 and 4, 4 is belongs to R. You can see here these four pairs are present, 1, 1, 2, 2, 3, 3 and 4, 4. So it is reflexive. Second property, that is antisymmetric. The relation is antisymmetric as whenever A comma B and B comma A is belongs to R, we have A is equal to B. So in this case, A is related with B, B is related with A and A is equal to B. So this kind of pairs are present, four pairs are present, so this relation is antisymmetric relation. Third property is that transitive. The relation is transitive as whenever A comma B and B comma C is belongs to R, we have A comma C belongs to R. So example for in this relation, 4, 2 is belongs to R and 2, 1 is belongs to R. Then 4, 1 is also belongs to R. So this kind of pair is exist. That's why this relation is transitive also. As the relation is reflexive, antisymmetric and transitive, it is a partial order relation. Example 2. Show that the relation divides defined on N is a partial order relation. N means set of natural numbers, so reflexive. So we have to check the relation divides on natural number set, is it partial order relation or not. So we have to check properties one by one. Reflexive. We have a divides A for all A belongs to N. Therefore relation divides is reflexive. Means if you take any element from natural number set, it divides itself. That's why A comma A order pair we can add into the relation and it satisfied for all the elements from natural number set. So it is divides is a reflexive property, satisfied reflexive property. Second property is antisymmetric. Let A comma B comma C is belong to set of natural number such that A divides B. It implies B divides A if A is equal to B. So the relation is antisymmetric. So these pairs are exist. That's why if A divides B and B divides A, means A is equal to B. This property is satisfied. That's why this is antisymmetric relation. Third property is transitive. Let A comma B comma C is belongs to N such that A divides B and B divides C. Then A divides C. So this also true. Hence the relation is transitive. Thus the relation being reflexive, antisymmetric and transitive, the relation divides is a partial order relation. Let's see the next example of partial order relation. So in this we taken a subset. The relation subset of a set of inclusion is a partial ordering, or any collection is a partial ordering relation or not. So if a set A is there, so A subset A is a subset of itself. So A subset A for any set A is satisfying. That's why it is a reflexive. Subset is a subset, relation is a recursive. The second property, that is antisymmetric. If A is a subset of B and B is a subset of A, in that case B is equal to A. This will be true in case of subset relation. So that's why the relation of subset is antisymmetric. If A is subset of B and B is subset of C, in that case A is a subset of C. This property is also true. So that means relation of subset satisfying transitive property. So the relation subset on the set R of real number, that is reflexive, antisymmetric and transitive. Therefore relation of subset is a partial order relation. So this partial order relation we can show by using the diagram. So diagram is nothing but graphical representation of the relation, where we are using the directed edges from one element to another element if the order pair is present in the relation R. So this diagram we can convert into the simple form using the hash diagram. So hash diagram is basically used to convert this partial order relation into the simplest form of the diagram, where all the edges is pointed upward direction. So we'll see the in detail about hash diagram. So given any partial order relation defined on a finite set, it is possible to draw the directed graph so that all of these properties are satisfied. This makes it possible to associate a somewhat simpler graph called a hash diagram, a partial order relation defined on a finite set. So steps for converting diagram into hash diagram. So start with the directed graph of the relation in which all arrows pointed upward. Then start to eliminate step by step following things. First thing, you have to remove or eliminate loops at all the vertices, that is self loop you have to remove first. Then second step is that all arrows whose existence is implied by the transitive property. So we have to second step is we will remove the edges which is because of the transitivity. Then third step is that we have to remove the direction indicator on the arrows, that is the last steps. Then consider the example. Let A is equal to, A is a set which contain element 1, 2, 3, 9, 19, and consider the divides relation on A, that is A comma B belongs to A. If A divides B is equivalent to B is equal to K A for some integer K for all. So this is the divides relation on set A, and it is a partial order relation. So this partial order relation initially represented by the diagram. So you can see the diagram corresponding to the A divides B relation, that is partial order relation. So this is represented in diagram. So 1 is related with 2, 1 is related with 1, 2 is related with 2. These are the order pair from the relation. 2 is related with 18, because 2 divides 18, 18 divides itself, 1 divides 18, 1 divides 9, 1 divides 3, 3 divides 3, 9 divides 9, then 3 divides 18, 9 divides 18. So all these are the pairs or order pair from the partial order relation that of A divides on set A. So here should be 18 instead of 19. It is by mistake 19 is written. So this diagram of respective partial order relation A divides B is converted into the simple graph or diagram by using the hash diagram by applying the steps that is given here. First the loops are removed, that is self loops are removed. Then second step is that edges because of transitivity is removed, and third is arrows are removed. Then you will get this diagram, and it is in upward direction, means 1 divides 2, 2 divides 18, 1 divides 3, 3 divides 9, and 9 divides 18, in that fashion. So these are some example of hash diagram. So it is on the PO set, that is partial order relation 1, 2, 3, 4, 6. This is the set on which this divides relation is established, and it is a partial order relation. So with respect to this divides relation, this is the hash diagram for the given partial order relation, and this hash diagram step by step is converted into the simple graph, that is by applying the hash diagram steps. So you can see this is 1 divides 2, 2 divides 4, 4 divides 8, 1 divides 3, 3 divides 6, 6 divides 12. Again transitivity is also initially in the diagram. Then self loops are there. So step by step is applied. First step is to remove all these self loops. Then second step is remove the edges because of transitivity. Which is the edge because of transitivity? We can see that here, if 2 divides 4 and 4 divides 12, so 2 also divides 12. So this edge is because of the transitivity. All such type of edges is not appear in this last diagram. You can see 2 divides 4, 4 divides 12, so 2 divides 12 is not there. So this edges because of transitivity property is removed. So this is nothing but the final output of this, applying the hash diagram steps. In the same way, hash diagram for S is equal to 2, 3, 5. So hash diagram of this PO set PS with respect to subset. This relation between the element is a subset, and so you will get this partial order relation with respect to this property, that is subset. So initially phi is a subset of all the set. Then so here you can see that phi is a subset of 2, phi is a subset of 3, phi is a subset of 5. Then 2 is a subset of 2, 3, 2 is a subset of 2, 5, 3 is a subset of 3, 5, and 2, 3. Again 2, 5 is a subset of 2, 3, 5, 2, 3 is a subset of 2, 3, 5, and 3, 5 is a subset of set 2, 3, 5. So here self loop is not there, transitivity is also not there, and it is a final hash diagram after applying the all the steps of hash diagram algorithm. So it is hash diagram. Here also it is hash diagram. Here it is a relation of divides. 1 divides 2, 2 divides 6, 6 divides 30, 1 divides 3, 3 divides 6, and 6 divides 30. In the same way, 1 divides 5, 5 divides 15, 15 divides 30, 1 divides 5, 5 divides 10, and 10 divides 30. So it is on divides, and it is a subset of kind of relationship, and these are the final hash diagram which is obtained by applying the hash diagram algorithm. So using this hash diagram, we will see different properties, that is, or different bound, that is upper bound, lower bound, maximal element, minimal element, greatest upper bound, and all these things we will see in the next one.